It is amazing to be here. I want to thank Stephen for inviting me. To be clear, I don't consider myself a racketeer. I'm sort of a fan from the sidelines. But my roots are in PLT. Matthias was my advisor back at Rice University in 1990, 91. But then I failed out of Carnegie Mellon grad school and took a real job. But these days, I've recently retired after 21 years at Amazon. And I'd like to talk about two projects I worked on there. The first as co-designer and the second as sole perpetrator. And I apologize in advance for the terminology confusion and the impedance mismatch you will feel during this talk. I made some bad choices 18 years ago. I'll try to be clear when that comes up. In 2016, I joined the team at Amazon that ran Amazon Retail Systems' entire catalog system. Is extremely complex Java service sitting on top of what we understood to be one of the largest Oracle database clusters in existence. It was so large, in fact, that it was crashing on an increasing cadence, and we knew we had to get off of it. So we set out to rewrite the entire system from the ground up. But this time, instead of using a relational database to hold all this, we would store it all as documents in the relatively new Amazon S3 storage system. While this is standard architecture today, in 2006, this was pretty bleeding edge. In a relational architecture, the interface to your data is SQL and the schema represented in it. But with the document store, the data format itself becomes the critical interface. That serialization form supports your entire ecosystem. It determines the universe of data that you can represent and the performance characteristics of using it. So both the format and the chosen document schema can have a huge impact on performance and complexity. So we spent a lot of time choosing a format, and we tried to do so holistically by looking at all the data surrounding the service. Now, when you look at a whole system, you find a lot of serialized data supporting many use cases. Beside your primary document store, you've got, of course, the schema for those documents and your services request response. You probably have an on-host cache. You might have an event stream for asynchronous data processing. You've got your configuration, maybe some dynamic business rules, and of course your logging and your monitoring. The list just goes on. And it's also likely that many of these use different formats, each of which is another library you need, more for developers to learn, and more tooling to build. Plus, each one of these has its own definition of what data is, which introduces risk that information will change subtly when moving from one to the other. At least inside Amazon, we often call this impedance mismatch. So we asked ourselves, is this really necessary? Is this bringing us business value, or is it adding friction? And really, what if we only needed one? What if we could orient our entire application around a single data format used for everything? What would such a thing look like? So we set out some design goals, or perhaps minimum requirements. So first, and most importantly, it had to have a really good data model. It had to have strong semantics of the types and shapes of data that we can represent. We're going to store this at scale, so we need to have a fast and compact binary format. We also want it to be able to work on the wire. But humans needed to get this, and humans need to author configuration and business rules. So we also needed a text encoding. So we wanted to also be able to be sure we could look at what the data was in our data stores accurately. So we needed to losslessly convert between these representations with no loss of fidelity. In 2007, we could not find a format that met this unique triangulation of features. So we spent the next year building what's now called Amazon Ion. Ion is a JSON-compatible data language. Ion text is a superset of JSON text, which means an Ion parser can parse Ion data with no problem. It can also encode it with very little trouble. It has equally expressive text and binary formats. As I said, you can convert across them with no loss of fidelity. Today, this is used everywhere throughout the Amazon retail system. including digital products. If you have a Kindle in your backpack, it's full of ion binary data. It's the primary Kindle book format. Our initial reference implementation was written in Java, but today there's implementations in many other languages, and it has been open source since April 2016. So let's take a look at some ion data. So we start out, this doesn't quite look like JSON, but it should be close enough that you can get a good idea for it. We have all of JSON's data types for free, but two are worth pointing out for reasons that will become clear. In ion, these curly brace things are called structs, and these square bracket things are called lists. JSON calls those objects and arrays, and in retrospect, I should have stuck with those terms. Looking to other types, ion tries to clean up the mess that is JSON's numeric semantics, or lack thereof. So if a number has no decimal point, it is an integer. If it has a decimal point, it is a decimal, meaning base 10 floating point number. There's not an example here. There it is. But if there's an E exponent, then it is a binary floating point number. It also adds some types that are in very broad use and important to have sound semantics around, such as timestamps with local offsets, not time zones. And it has text and binary lobs, or large objects. These are just byte arrays, and in the binary format, they require no base64 encoding or anything, but in the text format, they do. Perhaps more interesting, we have symbols. Like strings, these are sequences of Unicode code points, but they are type distinct and syntactically distinct. Instead of double quotes, they use single quotes, or as you can see in the bottom, if they meet Java identifier syntax, they don't require quotes at all. So the field names are effectively symbols. They're not technically symbols, but they're effectively symbol tokens. And then the real kicker, the last interesting thing are these user type annotations, which are symbols that can precede any value in the data model. As the name suggests, they're typically used by an application to communicate more complete schema information. In this case, it's giving a complete version schema to saying what this record is intended to represent. So the interesting thing, most interesting one for this talk, is support for S expressions. S expressions are a first-class data type in ION, added specifically to enable encoding of configuration, business rules, and so on. Semantically, they're just like lists. They are sequences of values. Notationally, they are different in text. They have parentheses instead of square brackets and commas. Now, to be clear, S expressions have no meaning to ION itself. They don't affect the parser in any way. It's just data. It's up to the application to decide what it means. Now, even though I pushed for their inclusion in the language, I was surprised how fast it took off. Our S expressions. It's probably obvious to the people in this room, but when you've got a parser with S expressions and a lot of data types, it becomes really easy to spin up a little language that manipulates your data. These came in two general varieties, as I learned over the next few years. Some wrote full homegrown evaluators. The catalog system did this for workflows, for product attribute normalization and validation, and half a dozen other domains. But the vast majority of our customers hacked up a prototype query language that was just written to demonstrate the efficacy of DSL, of the S expressions, but it made it into production. This caused a number of issues. First of all, the query language had no abstraction mechanisms whatsoever, which made the code very verbose. You could add functions and syntax if you wrote it in Java and plugged it in. But beyond that, there was no modularity functions in language, so you really couldn't reuse code. And of course, there was no editor support, debugging, or anything like that. Things are pretty rough, and the domain-specific languages in this scenario were awkward at best. But people liked it, and they kept doing it, and they kept asking us to be better. And so after several years of this, I decided to ask another big question. What if we built an ion-centric general-purpose language that we could use to build DSLs? And I think you know where I'm going with this, right? So I shopped this idea around as we do at Amazon. I wrote lots of documents and presented them to engineers and leadership. And to my complete surprise, the project was funded. And in 2012, I started building what's now known as Ion Fusion. Ion Fusion is a Racket-like general-purpose language built on the JDK. Its core data types align with ions. Its source code is ion data. And its goals are to streamline ion data processing in general and to support creating ion-centric domain-specific languages. Like Ion is used in a variety of Amazon and retail systems, especially those in the digital goods section. I'm going to start by looking at Ion's core data types. Here they are. They're just, Fusion's core data types and is the same as an Ion. Not really worth talking about. Those are the scalar types. The collections are a lot more interesting because they have operational characteristics that had to be designed. So Fusion lists, the square bracket things, are equivalent to Racket vectors, so they're random access. Fusion S expressions are equivalent to Racket lists, they're chains of pairs. Fusion structs are symbol-keyed multi-maps, the multi because JSON. To make this whole thing usable as a programming language, all of these collections can hold any kind of value, including procedures, whatever, and not just the Ion types. So here's our first example of Fusion code. So this reads those student records from standard input, grabs the name out of each one and prints it out to standard output. Again, this is Ion data. This was just a .ion file. And the student here is an Ion struct, so it's one of those multi-map things. And the dot operator is kind of a generic method over collections that allows you to pull fields or other elements out of them. So it's a reasonable time to talk about I/O because obviously we've adapted the protocol of the reader and writer from Racket. So read decodes an Ion stream and spits back Ion values one at a time. In the other direction, ionize encodes data into a valid Ion stream. If you give it something that's not one of those types I talked about anywhere in the data structure, it will raise an exception. Somewhere in the middle is write, which generates Ion-ish text. It won't throw an exception, but if it hits something outside of those value types, it prints things in these triple curly brackets, which won't parse if you feed that back into the Ion parser, but you can read it as a human being. The collections library is functional and immutable by default, even though the language is not really functional and not really immutable, but the core language wants to guide users in that direction. The library and terminology is heavily inspired by Dylan, of which I am a big fan. The primary APIs are largely generic methods. Like I said, dot worked on any type of collection. I did this because I feel like this gives a lot less surface area for developers to learn, and it's shown to be generally easier for folks coming from an object-oriented background there because they're kind of used to thinking in that way. But there's also type-specific alternatives for most of these things if you need performance and want to avoid the dispatch. Here's another chunk of Fusion code. I copied this straight out of the standard library. It's the implementation of the generic map. Again, you should be able to read this with no problem. As you can see, it checks whether it's given a list or an S expression, and then uses the appropriate algorithm based on that data structure. So in one case, it'll random access through it. In the other case, it'll recurse. And yes, we do have tail call elimination. Stepping back to talk about how Racket has influenced the design of Fusion, We have modules and namespaces, which should have identical semantics to what Racket does. We've got a macro system, although only up to the level of defined syntax at this point. We've got parameters. We have basic records, which Racket would call structs. We have series, which Racket would call sequences, and a decent selection of 4 comprehensions, which I think is a pretty great thing to have for data processing in general. And a whole bunch of other things that were borrowed over. In a lot of these cases, the implementation is pretty basic, right? It's just sort of the fundamental bits and pieces, though I've worked really hard to document carefully to be forward compatible if we want to come back and add functionality later. To be clear, I borrowed design but not code for various reasons. I really didn't look at the code. I read documentation and worked backwards from there. I did at one point look into the macro hygiene, the old implementation, to try to make sense of that. It really didn't help. I am dying to rewrite it all in terms of the scope sets at some point here. I did the 4 comprehensions I manually ported from the Racket source code to sort of work down to define syntax level and to get, we also don't have keywords yet, so a lot of stuff I could just sort of skip over. So this weird mashup of the language, of course, has some wonky corners. Syntactically, Ion is very different from Racket code. As I noted, to remain unquoted, symbols have to work like Java or C identifiers, which means a bunch of things from Racket have to be renamed. Like foo question mark would parse inside an S expression as 2 separate tokens, which I didn't want to deal with. So question marks generally become is underscore prefixes. Exclamation points generally become underscore M suffixes for mutate. The star and slash kind of, I pick a name on an ad hoc basis. There's also no glyphs like the single quote, backtick, comma for quotes and unquotes, which is gross. I will probably end up using very short annotations for that purpose, and I've built a prototype on that. It works out pretty well. Wonky corners in the semantics. I didn't mention it before, but Ion, for reasons, has null values in each type that are all distinct, including a null type. Fusion's is null function says true for all of them, but old-time schemers might be confused because null.s expression is different from the empty s expression. So is null of empty s expression is false. And of course, as I mentioned, any of these core data types can have annotations attached to them, and there's operators to pull those off and so on. But it does have impact on the implementation because even things like integers, the implementation has to be prepared for these things to be there. Thankfully, none of this stuff is used very broadly in like the data you would be munging through on a day-to-day basis, and the library kind of smooths over it, and it turns out to not be that big of a deal. Speaking of null annotations, let's look at a far more interesting Fusion DSL. This is the slide I am most proud to show off to this audience. So here's some code. I don't expect you to read this. This is a Fusion module that defines Ion's data model using denotational semantics via a DSL that I built for that purpose. This is that same source code running through a Fusion port of Lisp to TeX. So it just takes the syntax objects, prints them, configured to spit this out. What's even more cool is this is executable. It's strongly typed. The if and let down here at the bottom are not the normal if and let. Those are functional variants that know how to type check things and pass through the bottom value as you usually do. This model does sort of a lot of typical denotational semantic hacks to make it even vaguely readable. And then to go one step further, very quickly we built yet another DSL to express conformance tests for ION. And so you can run any ION implementation or the semantic model through this to double check that everything is working as expected. Going back to the semantic model code, I want to highlight how Fusion handles module paths. Fusion arranges all of its namespaces in a hierarchical address system. The default language, the sibling to hashlang racket, would be hashlang, although we don't have that, /Fusion. The entire Fusion standard libraries and submodules of that, for example, the generic collections are all collected or provided by Fusion/collection, unsafe list operators are under Fusion unsafe list, and so on. Obviously very Java-inspired. It gives you a nice way to organize things. It really helps in terms of documentation because you can have a landing page for each one of these. And it's expected that sort of user code would use the same sort of reverse DNS protocol that Java does. These are effectively paths into a virtual file system that encompasses all of the namespaces available to the runtime. And in your source tree, the file paths, just like Java, map back into this hierarchy. Now you'll note I did say namespace here and not module. So top-level namespaces are assigned synthetic addresses that have numeric components in them that are not valid module names. And so if at top level you declare a module called myModule, you'll end up with an address that has this numeric component in the middle. And what that means is you can't require that because it's not a valid module path, even though it's a valid namespace address. So it keeps everything sort of secure as the normal racket semantics would be for top-level modules. So why did I do this? Well, first of all, because I found the module path syntax in Racket to be incomprehensible. This was also inspired by a different system I worked on 20 years ago. But it's a very uniform syntax for however things come in. Decoupling the module paths in code from module acquisition, or how things are deployed and how they get into the execution environment, is really based on lessons I've learned at Amazon and looking at Java code and looking at how hard it is to vendor and sort of encapsulate things. And you very often want to swap pieces in and out in order to patch things. And it's just super hard when there's a direct coupling between the code and where that referenced code comes from. So, and I also see this as foundation for future work in dependency management, module versioning, and so on. I'll go really quickly from here. This is all in Java 8. You can embed it in your Java code. There's sort of basic sandboxing if you're evaluating untrusted code. There's a CLI and a basic REPL. The compiler doesn't generate bytecode. It generates a fast interpreter tree. I thank Christian for Lisp in small pieces. I'm up to chapter 6. The performance has been surprisingly sufficient, I think because sorry, I'm getting lost here. Because my implementation of structs is much faster and skips a lot of the work that you would have going at it the normal way in Java. We've got a unit test framework that's modeled after rack unit checks, code coverage tooling that's macro aware, reference docs generated from source code, and I'll say support for syntax highlighting plugins. I won't say we have a plugin. The Eclipse plugin we wrote stopped working several years ago after most Amazon developers moved to IntelliJ. This is now open source as of April 2025 as an independent project. It's no longer controlled by Amazon. It's controlled by myself and a couple other current and former Amazonians who have been involved with the project for a decade. We're building up our infrastructure for development, having to redo all this stuff that we got for free at Amazon. I'm currently hyper-focused on getting the onboarding experience to be nice, making it easy to try it out, to do ad hoc scripts. If you want to munch through some JSON code, you can use Fusion to do that. And long-term, trying to get this toward a stable 1.0 release, getting rid of a lot of cruft that we couldn't really get rid of at Amazon. And with that, and almost over time, thank you. I invite you to give it a shot. Our homepage is incredibly basic, but there's links to the documentation, to our Discord. There's an online playground. Again, it's all sort of very early days for this in the public sphere. Try it out. I'd love to hear any feedback you have. I didn't quite get an announcement list set up, but if you're interested in at most one email a month on this project, drop me an email and I'll get you added to that list in the next week or so. I'm at 25 minutes, so I'm sorry, but thank you.
Awesome. We got time for some questions? Where did you find that you decided, no, I don't want to go the way Racket or Racket V1 did this?
I think the module hierarchy stuff was the biggest. I think it's the most interesting thing I contributed here, and that's why I spent probably too much time on that. And maybe next year I'll have more of the sort of future stuff that I could talk about. But certainly coming from somebody who spent a lot of time dealing with a very, very large code base and seeing what it takes to keep that alive over time and specifically to keep it updated in terms of its dependencies, we need as an industry to have better mechanisms for that. And I think I have line of sight for a way to do that. Not that I think Rackets is bad, because again, I don't have a lot of experience, but at least coming as an outsider, trying to understand all of those subtleties, I found it kind of complicated. And I also just haven't seen some of the supply chain security stuff that we're going to need eventually.
I've also seen new language communities. It seems like it's been a struggle to get enough mind share sometimes. What do you see as the niche for this, the value that other languages or tooling can't supply right now?
TS has a question back there. I think there's opportunity for languages that are way simpler. And, you know, I got rid of 5 slides that are all about the nature of business software, and it's all just munging data, right? It's all just like getting data in and shuffling through it and filtering it and transforming it and shoveling it out the other side. If you've worked with AWS, you know that it's all these Legos and it still requires lots of glue, and all that glue is just what I'm talking about. So we do similar. Fusion plays that role inside Amazon in a few places, not a lot. But I do think there's opportunities there. And I think the combination of having a really powerful and expressive data language and a programming language that's tied to it just eliminates a lot of things. I think it's the combination there that's really the magic sauce, and it's why I continue to pursue it.
Are you allowed to talk about how Amazon uses technically? Are you allowed to talk about how it fails socially? And can you compare this to Clojure, which has its own data type manipulation the same way that you have that here?
I can't talk about Clojure because I can't really, I haven't really used it. They sort of grew up in parallel, as did Ion itself with many other data formats. I am totally willing to talk about sort of the social context inside Amazon and the good and bad things of that.
Before we go social,
not a live stream.
Not a live stream, okay.
So,
one thing that I don't see in the data model is unions of any kind. Those are obviously hard to do in a serialized data format, but I'm wondering if you have any thoughts about that.
Yeah, I mean, personally, I don't see that. I see that more as sort of a dynamic concern than a static concern. But Ion, sort of by a deliberate design choice, is strictly hierarchical. There's like no references or anything like that, largely because we felt like that was complexity that should be hoisted up a level and sort of left to an application.
Like choice.
Yeah, but I mean, this isn't schema, right? This is just data. It is what it is. And so there's really, other than the typed nulls, which are there to sort of say this value is not present, but if it was, it would be of this type. I don't at the moment see how unions fit into that, but maybe we should talk about that.
I'm curious about the implementation. You mentioned that it's an interpreter running on the JVM. Is it like a threaded, or are you just interpreting like an AST?
There is a compile phase, and it sort of does all of the sort of binding determinations, and it sort of spits out a tree of nodes that are just evaled with a store, and then at that point all variables are turned into integer addresses. Does that answer the question?
Yeah.
I don't think it's. I think a thread interpreter is something different.
Yeah, that
I would really like to start working on a bytecode compiler, or to just sort of refactor the whole thing so we could spit out WASM or something like that.
Well, that'd be interesting. WASM has table calls now.
The part I didn't say in the talk is that I worked on this full time from 2012 to about 2015, when the team that owned Fusion and Ion was disbanded. And then since then, I've just been maintaining it. It's been in production, but not funded. And so I've just been maintaining it because I enjoy it. So that's why, given the span of time, you would think things were further along than they would be. But now I don't have anything else to do. So
It might be interesting to take a look at truffle framework for JVM implementations.
The position I left at Amazon was with Amazon's JDK team, and I was working on bringing Grow into Amazon's infrastructure. So I'm got my eyes on that for sure.
All right, let's thank our speaker one more time.
Thank you.